Hi, this is Sayyab bin Rayan. I would like to welcome distinguished scholars from all over the world to listen this presentation. So before I begin, I must thank ESIS, a European Structural Integrity Society, for arranging this conference online. It's really a great initiative and a great help for students like me who cannot travel and I cannot attend the conferences physically at this pandemic situation. So let me begin. So this is a topic that we are going to discuss today, modeling of elastic properties for unidirectional composite materials using Ansys Material Designer. So Ansys Material Designer is a new software branch of Ansys. So we will see how well it predicts those elastic constants for unidirectional composite materials. This is me, Sayyab bin Rahan, along with me, MD Mazedur Rahman, and both of us have contributed same for the research outcomes. And we are from Northwestern Polytechnical University, which is located at Xi'an, China. So these are the research contents. At first, we will introduce you with the problem. Some basic definitions will be discussed. Then we will go to the main objective of the research. Then we will see how ANSYS is going to solve the problems. And finally, we will discuss our results and we will compare them with the available literature results to see how well those predictions are. So let me introduce you with the problem at first. So the definition we must know before we begin the RVE and homogenization. RVE is the representative volume element. This is the minimal representative volume that contains both the matrix and fiber in a sufficient way so that it can be used for further prediction of elastic constants. But let me describe this in a more clear way. So we have fiber and matrix. They are completely different materials. Usually the fibers are orthotropic. In some cases it may be isotropic, but the fibers, they are load carrying elements, and the matrix is just binding those fibers. This is the they are completely different material, and we want a singular elastic constant for this unidirectional ply. That is the reason why we will use the homogenization technique to find out the elastic properties. So let us see what are the elastic properties that we are going to predict. So these are the five elastic constants. We are going to predict the modulus of elasticity in the fiber direction. Then we have modulus of elasticity in the direction transverse to the fiber. And then we have in-plane shear modulus, out-of-plane shear modulus, and in-plane Poisson's ratio. Let us see some of the theoretical methods that can also estimate the elastic constants. We have rule of mixture. This is really the classic one, but unfortunately it can't predict the out-of-plane shear modulus results. Then we have modified rule of mixture, Halpin psi, Shamis model, EAM or elastic approach model, self-consistent model, Mori-Tanaka model, and bridging model. So this model actually they came one after another so that the predictions of elastic constants can be better, and it matches with the experiment. So this is the finite element problem. Actually, finite element can also be used to predict those elastic constants. The main problem is that the complex geometry and the boundary condition that we are going to set. So we will see how ANSYS is doing with the prediction. So the main objective of the research. So we will adapt ANSYS to calculate those elastic constants. Next, we will compare the predicted values with the experimental data available in literature. Then we will compare the predicted values with theoretical and finite element data available in literature. And finally, we will try to understand how well Ansys is predicting those elastic constants for unidirectional composite materials. And one thing we must notice here is that when we are talking about some error percentage, of course the experimental data will be used as a standard. So we must give some input to ANSYS to calculate the elastic constants. These are the inputs we have taken. Actually, we have taken the carbon and polyethylene as fiber materials. These are the two fiber materials we will study. We have taken those values available in literature because we are going to compare those results with the literature. So it is important to take those values. And we have matrix material properties here. As we can see, two different epoxies will be used. One will be used for carbon, another one will be used for polyethylene. And as we have told earlier, the carbon and polyethylene both fibers are orthotropic, and the matrix materials here these are isotropic. And we must define the fiber volume fraction. Along with the fiber volume fraction, we must define other things like the RVE shape. So for unidirectional composite material, as we can see, there are three different RV shape that we need to use. The first RV shape is a square, then the second one is the diamond shape and hexagonal shape. We will see ANSYS sometimes predict slightly different results for using three different RVEs. Finally, the boundary condition that we have already discussed, it is a bit tedious for other finite element solutions, but ANSYS has just helped us not to worry about the boundary condition, because these periodic boundary conditions are automatically set by ANSYS, so we don't need to worry about those things. Next, we will go to the results section. So first we will look at the result at Young's modulus for fiber direction for carbon epoxy. So as we can see the results are pretty close with the experiments here. Actually all the models are predicting pretty same results for Young's modulus in fiber direction, as you can see. In terms of experiment, we can conclude that the results are pretty close, and the error percentage is within 5%. So this is a good prediction. Next, we will look at the results of polyethylene epoxy. And as you can see, results are pretty similar for all the methods we have taken, and ANSYS results are pretty close with the experiments. There's green dots of the experimental results, as we can see. Then we will go to the results of transverse direction Young's. So these are the results for carbon epoxy transverse Young's modulus. As we can see, this time different models are predicting quite different results, and ANSYS is also predicting slightly different results for three different RV shapes, as we have described earlier. But the results are same when the fiber volume fraction is low. When the fiber volume fraction is high, and these results are a bit different, but not that much. I mean, within 1 to 2% limit, there's differences. And the experimental result, in terms of experimental results, we can see the ANSYS is predicting quite well, especially the square. This is the square shaped, the higher predictions are the square shaped prediction. So as we can see, the ANSYS square shaped RVs are predicting quite good results with the experiment. And for other Finite element method like the console, as you can see, it is predicting pretty high results for the square shaped RVE. So we can conclude Ansys is predicting pretty good result with the experiments. So this is the graph for Young's modulus in transverse direction. We have Ansys results here, the red crosses, as you can see, and we have experimental results. Even though it looks like the results are a bit far from each other, actually it is not, because if we look at the scale factors here, these results are not far from each other. So in terms of error percent, this error percent is not high, it's within 5% limit. So we can conclude Ansys is predicting pretty good results in this case. And of course we need to add one more thing, that is the square diamond and hexagonal shapes, they are predicting same results for polyethylene epoxy. So and this is the graph for in-plane shear modulus of carbon epoxy. As you can see, Ansys is predicting once again slightly different results for three different RVEs, but these results are pretty close with the experiment, and none of the cases we have found where the error percent is more than 5%. So we can say this is predicting quite good results here also for the in-plane shear modulus results. So this is the graph for shear modulus, in-plane shear modulus for polyethylene epoxy. As we can see, there's the experimental data, and this red dots here, there's Ansys predictions. So we can see the Ansys predicts quite well with the experiments once again. This is actually, it looks again that this data are a bit far, and Ansys is predicting a little bit higher, which is true, but looking at the scale factor here, these values are not far from each other, and the error percentage is of course within the limit of 5%, which is excellent in terms of agreement. So this is out of plane shear modulus data for carbon epoxy. As you can see, Ansys is predicting three different values for three different RV shapes, and these are the experimental data we can see. And as the previous case, fiber volume fraction goes higher, and the predictions of three different RV shapes and the differences among them, it goes a little bit far from each other. And we can again conclude that the square shaped RVs are more closer to the experiments, and we can also say that the error percentage has not exceed the 10% limit here. So looking at the scale factor, the error percentage has never exceeded 10%. So this in terms of agreement, we can say this is a good agreement with the experiment. So this is out of plane shear modulus for polyethylene epoxy. As we can see, these are the results for experiments, the blue dots, and we have the red crosses for Ansys results, and these results are again within a limit of 5% difference, which is quite good. Then we have the in-plane Poisson's ratio results. So as we can see, unfortunately we do not have available data for experiments, but all the models, they are predicting almost similar results. They are quite similar to each other, and Ansys is predicting, these are the red dot results, this is what Ansys is predicting. And from the previous experience, we can conclude that Ansys is predicting pretty good results in terms of predicting the Poisson's ratio. Then Let us conclude this presentation with the key findings. So, of course, Ansys can be a good option to define the elastic properties of unidirectional composite materials. As we have seen, most of the cases it is predicting pretty good results within a 5% error limit with the experiment, which is excellent. And in rare cases, it is predicting higher values than the experiment, but this limit has never crossed 10%. So in terms of agreement, this is good. Next we have solution timing actually. So as you can see, the timing is pretty fast. Only takes half a second for a single solution. Since we don't need to design anything, we can input those data, and we can guide Ansys to select RVs. That is the reason why the solution is pretty fast, and we have used a personal desktop for this solution. And then we have Ansys Material Designer that provides similarly results with the bridging model. So if we go back, we can see the bridging model, which is one of the most popular used model to predict the effective elastic properties. The results from bridging model is pretty same with the Ansys Material Designer, which is a good indication that Ansys can be used as a software to define elastic properties of unidirectional composite materials. So this is what we want to do in future. We want to continue our investigation for woven composite material. In terms of complexity, woven composite material is complex than unidirectional composite material, of course. So this is the thing that I wanted to share with you. If you have any question, you can reach me. This is my email address. I would be glad to answer any question regarding this research, and I would like to thank you all for being patient and listen my presentation. Thank you. Have a nice day.